Alright, so let's get started. Welcome to Chenren's thesis defense. He has done a wonderful job, especially considering his thesis was done during my maternity leave, the sabbatical leave, a lot of other leaves. So I wasn't here that much during his thesis, but he did a great job, and which Howard helped a lot during the process. All right, let's get started.
All right. First of all, I'd like to thank you all for joining one of the biggest day in my life, my PhD defense. Today I'm going to talk about learning human context through unobtrusive methods. So there are three keywords: human context, learning, and unobtrusive. Human context is so important because it almost covers all the aspects, such as where I am, what I'm doing, and who I am with. It would be so great if the modern computing technique can automatically aware of this situation and do something useful for us. As a simple example to warm up, let's say one day you are on the way back. You have a smartphone. Today's smartphone is smart enough to know your location, your time, and speed, and further infer this context, such as you're driving, there's traffic ahead, and estimate how much time you still need to go home. And further, to reject incoming call for driving safety, plan alternative routes to avoid traffic, and also preheat your room and pre-cook your meal to make sure they are ready for you at the right time. So here, as you can see, this context actually bridges the gap between the sensing and the action in such a way that it reasons the raw sensor data and then do some smart inference for this action to do something actually implement something useful in software and hardware for us. Smartphone is just one example. In very near soon, you will see all these glass necklace, watch, wristband, they're all smart. And if you go to Bay Area, actually, everyone is wearing this Fitbit. So all these sensors, smart sensors devices work together. They provide us better sensing coverage for diversity and accuracy, and work together to help us to understand ourselves better. If you look at the right side, as Yang yesterday introduced, Vigo is a very successful reason to kickstart the project. If you wear it, it sort of tells your energy level. So as a PhD student, if you know now your energy is very high, you're supposed to work on very hard research projects. If you are low, then I think WinLab faculty are so nice. They don't mind if you take a snap.
No, you should be looking at other things, working on other things.
That's a good answer. As a Fitbit, I don't think I need to spend too much words. If you wear it, it counts how many steps you walk, monitor if you are sleeping well, everything together, fuse all these functions in one small devices.
Does your thesis examine the loss of Fitbits and solve that problem? Because everyone I know has lost their Fitbit at least twice.
That's a context too.
Yeah. Anyway, go on.
Yes. Detection. It's essentially a fall detector. If it detects a fall, it will trigger the alarm to the care center, so people there will notify it. But the problem is, usually, often elderly need to wear it. But if you are getting very old, the problem is very often you don't remember to wear it. So here, hopefully I convince you learning human context is very important. But here we want to ask such a question. Can we learn this human context in a more relatively unobtrusive manner? What I mean by unobtrusive is no need to wear a device. Most modern techniques assume or require you to wear such a device, such as, for example, the smartphone. But usually that's not the case when you go home. When you go home, I think everybody has this situation. You put your phone in a random location and just go anywhere. No extensive calibration. So in the domain of human-centered computing, the characteristic of each human, whether voice or activity, is not uniformly is not uniform. So, of course, the system, you can profile the system with every possible scenario with different combination of different human, but it's very labor extensive. And also, no need to report status manually. In the domain of social science, for example, psychology or HCI, human-computer interaction, usually it requires a detailed design, plan, and evaluation. And usually you use audio and video recording in the experiments, and then hire some volunteer to replay, to tell if are you happy or something else. But this is usually again, it's very labor intensive and not necessarily accurate. Overall, we want to overcome all this stuff, and in the vision of Mark Weiser's ubiquitous computing, this ambient intelligence should be transparent to all the user and naturally take place to monitor our physical activity and social activity. So today I'm going to mainly talk about two techniques to fit into the roles I just mentioned. The first set of work is called radio frequency-based device-free localization. Essentially, it's a localization technique to track your location, trajectory, and speed, your physical activity. It is a human localization technique. It directly localizes the human. It's different from most, I just mentioned before, the device-based localization. Device-based localization is essentially you assume people always carry a device, so they are always co-located, and you actually locate the device, not human itself. But here, the device-free localization technique can track you wherever you are, whether you carry the device or not, especially at home. This application could be very useful. For example, it can count how many times you go to the bathroom at night, and then detect how long you have been stuck in the restroom. And also, another point I want to make is we actually do a survey in the elder care center. Most of the people don't want to carry any device when they are at home, stay at home. So let me give you a simple example to show you how it works. In fact, in our daily life, we are constantly exposed to lots of radio waves. And in fact, our presence will interfere with the radio propagation and end up with a change on the received signal strength. So in this simple example, let's say this is your home. You have a wireless AP, you have a door sensor. And then when the room is empty, you have a wireless link look like that. When you show up in this room, you interfere with the radio propagation and end up with a change on the received signal strength. So you capture that change. And in fact, you have your phone, your laptop, and eventually your TV and your couch will be smart. So all of them will have this wireless interface. And what they do is they will just wirelessly interconnected in the vision of Internet of Things. So you have more link, more dimension in this problem. And the fact is, wherever you go, as long as you change certain level of the signal strength of some subsets of this link, then this information can sort of differentiate location to location to eventually tell you where you are. However, here you might ask a question. If I touch the line of sight, then do I definitely make a change? That's a common sense for the infrared motion sensor. So if you remember, even at WinLab, we see such a motion sensor, and then essentially it creates a beam. As long as you pass by, you touch the line of sight, you make a binary change on this sensor data. So it's a geometry problem. As long as you have enough beam, then you simply capture the intersection of all the links has such a binary change to determine your location. But in radio propagation, unfortunately, especially in indoor environment, it's not the case. Because the multipath, I guess everyone here understands what is multipath. So what it means is when the radio is transmitting, it's broadcasting, it's transmitting omnidirectionally. And in indoor environments, you actually have lots of reflector. So this wall and ground can all be this reflector to create this kind of multipath. So when the transmitter talks to the receiver, it actually not only transmits through this line of sight, but also through this non-line of sight. So they end up with, as long as you touch any part of this non-line of sight, there's still a chance you can change the radio, some part of this radio propagation, and end up with a change on the received signal strength. So sometimes you may increase the signal strength. Sometimes you even didn't, even you block the line of sight, you didn't change the signal strength at all. So this indoor multipaths make this device-free localization as a very challenging problem. So if geometry-based method doesn't work, you go for learning, you go to site survey. You need to collect the empirical data from location to location to learn this environment. In this, in the domain of localization problem, it's called fingerprinting. So essentially, you slice this, you predefine a set of points, and then go to each point to collect the signal strengths and create such a database. And then each entry store the location, the pair of location and the signal strengths. And in the testing, you just appear in a random location. You take your RSS measurements and then do the best matching. Here we do something slightly different. We slice the room into a different into a grid of cells. Each cell is context-based, such as here, such as the bed, and this is a bed, this is a couch, and this is the desk. Because in our daily life, we care more about what we are doing. This context information can give us more information we care about. So this is what we call cell-based stochastic fingerprinting. In this fingerprinting case, we draw these two XY axis as the RSS measurements from two links. Let's assume this room only has 2 links. And then for each cell, I make random movements to collect all these data. So the red points means the RSS measurements when I was in different location in cell 1. Same thing happened in cell 2 and 3. So this cell-based localization actually gives us several benefits. The first one, as I mentioned before, is context. It allows the context-aware-based location definition, such as this context information, instead of the X and Y coordinates, because if we just know the X and Y, we have no idea what that means. And also, instead of collecting hundreds of points, we only need to train tens of cells, which significantly reduce the calibration effort in this fingerprint site survey process. And also, since we discretize the physical space, we can formulate this problem into a supervised machine learning problem. So we, in terms of this supervised machine learning problem, we choose the basic algorithms called linear discriminant analysis. Essentially, it treats RSS measurements with a person's presence in each cell as a class. And then each class is assumed as a multivariate Gaussian with a common covariance. So as you can see, we collect, in the training phase, we collect this data from different cells. And then the linear discriminant function essentially draws this linear hyperplane to separate these data sets from cell to cell. And in implementation, in fact, after the training phase, I collect data from cell to cell and then build a classifier. So in the testing phase, I put myself in a random location, take the RSS measurements and plug into this classifier. Each class will give me a value. I choose the value. I choose the cell or the class which gives me the maximum value as my predicted location, estimated location. This is the evaluation platform, thanks Rob and Ben. As you can see, this is a layer system. The sensing layer, from bottom to top, from the sensing layer, collect all these different kinds of sensor data and push this data to the distributed aggregator. And the aggregator serves this data to the analysis layer. Analysis layer, essentially, a different user can write different solver to subscribe the data based on their need and provide the solution, for example, device-free location data to the world model, and eventually present this data through a world model to the real user. So for my job, I only need to focus on this part. And this is our home-made tag. This is a transmitter, this is a receiver. So the transmitter is transmit only. It's just broadcast, no CSMA, no carrier sensing. The receiver receives the data, forward this data through a USB through a distributed network hub, eventually to a centralized server or cloud service. For the hardware, we use MSP430 as the microcontroller unit, and CCL01 as the radio chip. If we transmit 2 or 3 packets per second, the battery, if we use a coin cell battery, battery life could achieve to 1 year. We also developed other sensing applications such as door sensor, wall sensor, Rob and Ben have been doing, and also the infrared sensor to estimate the relative ranging and angle estimation. Ashwin and I work with. So this is the first deployment I test my system. This is a room before I get married. As you can see, I make it very cluttered. so to increase the complexity of this.
So what was the beacon rate for these instruments?
This one actually at 4 times per second.
4 times.
Right. As you can see, this is the receiver, this is the tag, and this is the hub, and this is the laptop to collect the data.
So have you retrained since marriage?
Oh, we moved to a new place.
No, you're saying
Let's
it's
all
a
the
room
stuff
cleaner
go
than this.
I'm just saying.
Oh yeah. Yes. So yeah, this is small. Yeah, since I'm living alone, so it's a small apartment, 5 by 8 meter, and I slice the room into 32 cells. Use one host PC and 8 transmitter and receiver as the sensor devices. I train the system and collect 3,200 testing points from different places and test this system. I achieved 97% cell estimation accuracy and 0.36 meter localization error.
So what happened to the other eight cells? Like, because your room is 40 square meters, but you only have 32 cells.
Yeah, because
approximately. Some of the part, like the bed, this is bed. It's a little larger than.
What's the definition of cell estimation accuracy?
Oh, so it's the percentage of I correctly estimate the cell I'm located in. So if I test 100 times, but there's 97 times the system accurately predicts my location, then that's 97.
So it doesn't, when you're wrong, though, it doesn't matter how many cells you're wrong by, just that you're in the wrong one.
Yeah, it's just the wrong one. But if it's wrong, then I will count it as into the localization error. So if you remember before, I choose this stochastic fingerprinting, and traditionally people will use point-based calibration. So I evaluate the methods, different methods in this system as well. So if you look at different frequency, if I train the system using random walk, it's constantly better than if I stand still in each cell center to train the system, because in this process I sort of average the error caused by the multipass in these deep fadings. I average all these error, and also this results shows that if I choose a lower frequency, I will have a better results, because lower frequency means longer wavelengths, which means it's more robust to the small objects, robust to the interference from these small objects. If you look at this figure, this is another set of small experiments. When I walk from one end to the other end in this apartment, and I take the measurements, ISOS measurements at each point. As you can see, if I choose a lower frequency, I have a smoother change in this different location spatially. But I'm not saying I should always choose a lower frequency, because if the frequency goes very low, then the wavelength becomes very low. Even human factor will be ignored. So even human appear in this room, I will not make any change. It's all significant change to this radio link. Also, you might wonder if 16 devices is too much for this room. So here I plot the box plot when I use different combination of different total number of devices to calculate this cell estimation accuracy. As you can see here, if I only choose 8 devices, the best sets give me 90% cell estimation accuracy, which means what I do is actually I deploy this A transmitter, A receiver at a fixed location, and then in the offline process, I randomly took all the combination of different transmitter receiver, and then plot all these results for each box plot.
Is the zero meaningful? Does that just mean you chose all receivers or something?
Yeah.
So that's
Zero
not
means
really-
it doesn't work. I took A transmitter or A receiver.
I don't know if you want to show it that way.
And why, like, at the two ends, like, it's understandable, like, when you increase the number of devices, the cell estimation accuracy increases, right? And also with smaller variance.
Yeah.
Why on the other end, when you have smaller number of wireless devices, seems like, okay, the estimation accuracy is low, but the variance is also low.
Variance up because we don't have too many combinations. If I only have 2 devices or 3 devices, I don't have so many different combinations.
Oh, okay.
Yeah, in this part, yeah, the permutation, it's the combination, not permutation. Yeah.
Okay.
Right. And also, originally we take 100 samples in each cell. If you think that takes too long, because the more sample you take in each cell, the longer the training data it will take. So we actually also plot this arrow bar plot to show the number of different training measurements for each cell versus the cell estimation accuracy. We find out actually we only need a sample to get this small error bar with the 90% cell estimation accuracy, which means we actually only need only a few samples from each cell. That's enough to characterize the video propagation in each cell. And also in any indoor radio frequency-based indoor localization, we will have this long-term test problem, which means as time goes, the environment will keep changing. If we choose the fingerprinting approach, the training data I took today will look very different from, even for the same location, it will look very different from 1 or 2 months ago, 1 or 2 months later. So as we expected, if we take the training data and then just use this data to test the system 1 month ago, we only get 20% cell estimation accuracy. But if we play a little bit trick, which means in each testing, when the room is empty, we also take the RSS measurements as the baseline, and then we compare this value link by link with the data we took in the training phase. If we see there's a significant change, for example, larger than 6 dB, then we remove all these links from the whole system. Then we can achieve 90% cell estimation accuracy still. But this is not a very good a good solution always, because as you can see, as time goes, I need to keep removing all these links. Eventually, if I only have a transmitter, a receiver, which means I only have 64 links, I will lose all the links in the end. So at a certain point, I need to retrain the system.
Do you want to explain naive correction, the blue line?
Oh, naive correction. Naive correction means I didn't remove those bad links, but I only, for the training data and testing data, I used the RSS change. The raw RSS measurements minus the baseline when the room is empty.
Right, so you subtracted the baseline.
Right.
But you didn't remove it.
Right. But yeah, it gives 80%. It's not that bad. But if I remove those link has experienced significant change, then I'm able to achieve that. Right, what I just talked about is how to localize one person. And naturally, moving forward, if we really want to deploy the system to a real home, people will ask how do you deal with multiple people. So the challenge here is if we still use fingerprinting approach to train to tackle this problem, then we need to try all the different combination of different people. Then that will be a significant labor. I show a simple example here. So let's say you only have 9 cells in this room, and then if you only have one person, then you just move this person from cell to cell, it takes 9 trials in total. If you have 2 persons, then it has multiple rounds. In the first round, you make the first person standing here, and then move the second person from this cell to the end. And in the second round, you move the first person next to his next cell, and then move the second person from this location to towards that location. And it takes 36 trials for 2 people. Let's assume it takes 1 minute to train 1 cell. And then let's say if you're a bachelor, you want to save money, you live in a very small apartment, then it takes 9 minutes to train the system. And after you get married, you move to a bigger apartment, and it takes almost half day to train the system. And things can get even worse. After you have a kid, you move to a bigger house, and eventually it takes like 1/3 of the year. And I'm pretty sure nobody is going to take the effort to train the system.
So the idea was combinatorially do all the placements, make all the measurements?
Yeah, but that's something I try to avoid.
Yeah.
So instead, we ask such a question: can we use one person's training data to localize N people? Hopefully, then it will be very, very large. Yes, actually, our system has this localizing device-free localized multiple device-free people actually has 2 phases. First of all, we need to count how many people are there. The second step is to find their location. Because in device-based localization, localizing 1 person and multiple people is the same thing. Each device is beaconing to the system with a unique ID. But in device-free localization problem, when you have more people, they just interfere with the radio signal in a very messy way. So we need to count how many people are there, and then track their location. The intuition is that if we have more people, then they will cause larger impact on different links. So here's a simple example. Let's say we use link change as a notation as, how much you change when you appear compared with when the room is empty. So when the room is empty, you observe this 0 dB from these 3 links. So when you have only have 1 person on this location, then you affect these 2 links, you make certain dB change. When you appear in this location, you affect these 2 links, make certain change on these 2 locations, to these two links. When you have 2 people simultaneously in these 2 different locations, you cause a change to all the 3 links. In fact, you can see the link 2 actually, the change on link 2 becomes a little larger. So if we quickly summarize what we just observed, then as you can see, as the number of people increase, if we sum up all the RSS change from different links, we do observe increasing trend. And at least here we can say if we just use this delta n, the sum of the RSS change from all the links, we can say we can do a perfectly presence detection, because if we have some people in the room, then clearly there's an indicator, there's a sign. And also it seems that people cause additive effect on the radio links. So we are thinking this problem, can we reverse this process for counting? Since people are causing additive effects, as they people becomes more and more, they cause additive effects. So we are trying to localize them 1 by 1 and then extract their effect from the remaining links. Hopefully, iteratively, we can eventually find how many people are in this room. So let's say in this example, we have here what we observe is the RSS change from these 3 links, but we don't know how many people are there yet. And then we run our previous localization algorithm to find this guy's location, this set. And then we have the training data when there's only 1 person in this cell. And then we do the subtraction. And count plus, go to the next iteration. This is the remaining RSS measurements. And then we run our localization algorithm, find this guy, this location, and then check the training data for this location. and then do the subtraction. And here we find there's something wrong here because it shows a negative value, which means we over subtract the impact on this shared link, this link which is mutually affected by two people. If we do the simple math, we find if the link is only affected by one person, then that's fine. If the link is mutually affected by multiple people, then they sort of cause such a nonlinear effect. To correct this error, we propose this link, location link correlation. Essentially, it's a correlation for each link. It's the correlation between each cell divided by the normalized correlation for each for this location to the other all the other locations. And if the link is only cross one cell, then this coefficient will be very large. If the link cross multiple cells, then it will become very small. And essentially, this beta, this coefficient, this fuzzy parameter will be ranged from 0 to 1. And after we apply this this beta, this coefficient, we do the same thing again here. We find this guy, check the training data, and then multiply by the coefficient, do the subtraction. Go to the next round. Find this guy, check the training data, multiply by this coefficient, and that's clean up data. We have two people in this room. From high level, it's a sequential counting algorithm. Let's use this delta to denote the number of RSS change of all the links in each round. And in the very beginning, we will detect whether there's any remaining people in this room. If it's yes, then we continue. Then we assume there's only one person left, and then we run our localization algorithm to find this guy. And then subtract his impact, reference to the training data when there's only one person in that cell. And then do this subtraction link by link. And then go back.
So what's the termination algorithm? It's delta n is greater than
delta n is 0. Delta 0 is when there's nobody in the room, but 0, 1 is when there's one person in the room. It's the average value for the person appear in different settings. So sometimes we cannot, in real implementation, we can, when we do the sequential subtraction, we cannot get that clean data. So we compare the, when we, at the end of each round, we compare this remaining RSS with the data when there's only one person in.
Yeah, I'm just wondering, how do you set that threshold?
Delta 1.
Well, no, so.
Delta 1 is we collect the training data for
like,
one
so
person.
that's the one person training data. Okay.
Yeah. So now we know how many people are in this room, and we are ready to track their location. And the second property we observe is indoor human mobility actually have some constraints. For example, in the next moment, we cannot jump too far away. For example, in this location, in this scenario, if last moment I'm in this location, and then in the next moment, next 10 tick, let's say 1 second, I couldn't jump too far away, but I'm still free to go anywhere in this green ring. And if I'm in a cubic environment, this cubic actually constrained my human mobility in the next tick even more, which means it blocks, it eliminates the possibility for me to go to these 5 locations in the next moment. My choice is only bounded to these 4 choices. So we can use this property to sort of eliminate some possible scenario and then improve our localization tracking performance. So in this simple example, let's say we have one person, and then we take the measurements, plug into our localization algorithm. And this data likelihood shows the probability of each cell's occupancy. So if you look at this map, we find this cell has a maximum value of 0.2, which means the system tells I'm most likely in this location. But in fact, in last moment, actually I'm in this position, and there's no way for me to jump from this cell to that cell in one time tick. And here, this trajectory ring filter, the human mobility constraints sort of tell me the next moment I can only appear in these 4 locations. If I multiply by these 2 information, this is the observation model, this is the map information. If I combine these 2 map information together, it gives me a refined results, which sort of tell me, okay, this is the correct location I am in the next moment. So this example essentially shows the indoor human mobility constraints actually can be leveraged to improve our localization accuracy. The math behind it is simply the Viterbi algorithm. We model, in this tracking problem, we modeled this as a state transition problem. Basically, in such a Markov model, you have an observation model. You try to calculate the data likelihood. And also, this is for each state. And then you have state transition probability from state to state, from cell to cell. And in this process, you always remember how many people I keep tracking, and then just based on combine your observation, ISIS observation, and the state transition based on coming from the map information, and then decode the optimal path, the most likely path trajectory for all the people you have been keep tracking. So this time move our system to lab C. This is A wing at Wing Lab. It's 150 meters squared. I slide this room into 37 cells. As you can see, each unit this time becomes each cubic and or IO segments. I deploy 13 transmitter and 9 receiver in this room, and they create so many line of sight links. And this time I involve 4 people in this environment. As you can see, C is working this way independently. D is always sitting there. And A and B here have an intersection path. So this is the counting results. As I mentioned before, I realized this nonlinear effect when people mutually affect the real link. So I need to propose this location link coefficient to mitigate this error. So if I use this location link coefficient when I do the sequential subtraction, I can improve 30% accuracy compared with this baseline, which means actually if I'm not using this location link coefficient, I will undercount the number of people here. And if I use this location link coefficient, and let's look at the trajectory with different cases, non-overlap and overlap trajectory. We find out in the non-overlap trajectory, we achieve 85% counting percentage. And in the overlap trajectory, we are getting much worse results, because when people move very close to each other, then the system will look at as a very fat person. But this, there's certain...
Not much worse, right? It's worse. But I wouldn't say it's much worse.
Right. But yeah, but there's some way to improve that. In fact, use some continuous, in time domain, use some continuous context information. For example, if I see there are 2 people at last moment, and suddenly I only see 1 person, but nobody actually at that moment is very close to the door. So I can predict they actually merge to the same place. So in that case, I can still count there are 2 people in this room. For the localization results, if I use this trajectory ring filter, I achieve about 1 meter localization accuracy. This is expected. It's expected to be better than if I'm not using the trajectory ring filter. To quickly summarize our lessons learned from this work, device-free people's count and location actually can be tracked with high accuracy. This is the part of no need to wear device. And also, we demonstrate that actually we can use the data collected from one person to count and localize to track multiple people. So we didn't use extensive calibration. We don't need to try all the different location combinations from all the people to apply to the multiple people case. And also, although the indoor space brings more complex radio propagation because of all these obstacles, but actually give us other benefits. This obstacle sort of constrain some of our possible mobility constraints, and then we can use this property to further improve our localization accuracy. So that was this first part. This is the second part of my work. It's called supervised speaker counting on mobile devices. So in this work, essentially, the Crowd++ mobile application we have been developed, it can record audio conversation and automatically count how many people are talking in this conversation. You track your social activities. So here, what I mean by unsupervised is I don't need to collect all the speech characteristics for each person in this conversation beforehand. So here, let me push a few efforts to motivate this problem. Let's say you go to a new city, Zurich, for example, and then it's dinner time. You want to find a nice restaurant to have dinner with the friends you just make. Or where should you go? Usually, if you Google your map, then you will see this map, which essentially gives you all the possible restaurant locations. And then you might feel great if someone can give you such a augmented functionality, which means the size of each circle on top of the restaurants is proportional to the number of people there. Then, of course, you have different flavor. If you want to quickly finish your dinner, then you can choose this place. But for me, probably I want to find a restaurant with more people, because I assume if there's more people in this room, then the food quality, the service quality will be better.
Well, maybe it'll be worse because it'll be crowded. And noisy.
Pessimist.
But you could look at the derivative of that versus time at the end. L is pretty fast.
Do you know if someone going with you? You should know if someone is with you who's going with you, and then choose an appropriate restaurant for the pair.
Yeah, I assume if someone is local. But usually, if you go to a conference, people come from different places from the world. So, of course you can check Yelp. But this is an alternative approach. As parents, you might want to know if your kids are getting well with other kids, because especially when they're at school, because you cannot monitor them 24 hours per day. And if you know your kids look like that, then certainly you don't need to worry about anything. But there's always kids.
I think that you just don't know that. Parent, so your kid could look like that. You can look like that or not look, but they could be like that kid on the end is really good. Just saying, you gotta have a little skepticism here.
Do you have kids yet?
No.
Is it obvious?
What kind of degree?
This is
But go on.
This is an advanced degree I have here.
Well, he's a
Several
temp.
of you have it.
I'm from this class. I mean,
No, you're alive. You're passing.
Good attempt.
okay, keep on going. Just go fun stuff going.
So
Go to the next one.
Yes.
skip this one.
Yeah.
As students, of course, Roy's class is always have lots of interaction, I know, so I want to take his class. But if you know the class will look like that beforehand, definitely you don't want to take that class.
Yeah.
Professor.
Change professor, yeah. Yeah, next time I will put Roy's speaker.
She might give out bonuses for people raising their hands.
But they might just be so confused they all have to ask questions.
At least they're here.
Yeah, I guess
I heard in my class that that the reward you give for students when they catch mistake has gone up over the years.
Yeah, it's $1.
It's a
Dollar?
$1.
Wow.
Big mistake, I pay $1.
Problem is, Rutgers doesn't pay enough. They can afford that.
I don't make mistakes. Go on.
I don't want to brag, but I had out of 180, I had 146 responses to SIRS, my survey,
Whoa.
out of 180. But I actually bribed them. So.
Yeah, okay. Assume we want to solve this problem. Actually, there's one simple technique to solve this problem. It's called speaker count. Dinner time, where to go? Just find the places where most people are talking. Is a kids social? Just find how many different people they talk with every day. And you want to know which class is more attractive, just check how many students ask you a question. Different students ask you a question. So all you want is the speaker count, and all you need is essentially just one piece of microphone to record your audio data, and then feed that data into the microcomputer to do the data analysis to estimate the number of people, the number of speakers. And certainly we have some challenge. For example, we have no idea what's the speech characteristics from each speaker. And also in the real scenario, we will have some background noise. So if we only from the energy scale, we just do a simple thresholding, it's really hard to differentiate human speech and some loud background noise. And also, because we are going to process a whole few minutes conversation instead of just a few seconds, then we need to care about this energy efficiency problem, especially if we want to achieve real-time performance if we implement that system in a mobile phone. And also, since we are doing audio recording, then it's natural people will raise some privacy concern. Where are you going to upload my data? Are you going to upload the data to some third party, which I really hate, let's say NSA?
You don't have to upload it.
They upload
They
for
have
you.
We propose some solution to tackle all this challenge. First, we extract speaker-dependent feature, which means the feature will uniquely characterize each person's speech. And also, we will look at the frequency domain to look at the characteristics of each segments to see if it's come from human speech or just pure background noise. And also, we try to model in this problem. We use coarse-grained modeling to reduce the algorithm complexity and reduce the computational time. And also, all the computation will happen on the device. So, record audio, count the number of speakers, and then delete the raw data, and probably just upload the number of speakers from the device, nothing else. So this is the overview of the Crowd++. It's open. The source code is public here. If you are interested, feel free to download. It has multiple steps. The first step is always you use a microphone to record a raw audio sample, and then you do the FFT with the Hamming window to make the raw audio signal stationary. And then in this phase, when you have all this raw data ready, then you want to filter out all the non-speech segments because you only want to process the human speech part to count how many people are there. And then you extract the speaker-dependent feature, which I will cover later, MFCC and gender. And once you have all this information, you can feed all this information and data to the algorithm to unsupervisedly count the number of speakers in this conversation. Let me show you one by one.
So these are off-the-shelf algorithms that some people invented years ago, or are these algorithms you're inventing?
I think it's not complex, but I'm the first one to recognize there's the speaker counting problem is not well recognized and sort of important in some scenarios, so I did it.
So most of the fundamental algorithms were invented by speech community. We didn't do it, but we sort of do some stitching and the packing to make it suitable for our application.
So which of these boxes did you do and which did you get off the shelf?
Well, that's another way to talk about it. Yeah.
I think if you were asked for me or Larry,
You would have said, oh, I did all this.
but he might not have
except
said,
the last
So
one.
the
the
unsupervised
speaker
learning.
count he might not have said because the
that's-
problem that they were always looking at is you're speaking into a phone.
Yeah.
Right. Now, I would say, though, if you were to ask, like, one of the video conferencing companies, they might have had that sort of thing, because they usually had to track and change camera panning and stuff. But,
And also, they usually have this speaker's data beforehand. They try to do the segmentation to calculate when is the turn taking point. Yeah, so the first step is always speech detection. Try to extract which part of the speech is human voice. And then one common intuition is that human pitch, the pitch, we can actually use pitch to tell this information. And human voice is actually, the statistics shows the pitch of the human voice span from 50 to 450. So we apply the pitch estimation algorithm for each segments. If it's fall into this range, then we say it comes from the human speech. Otherwise, it's background noise. We filter it out. And for the speaker-dependent features, we use MFCC. We didn't invent anything new here. We just borrowed it. It's essentially the short-term power spectrum of the human speech characteristics. It's developed very mature and developed by the speech community. It's effective and efficient, so we just borrow it. It has been used to characterize different sounds and different people's speech. People have been working very hard to use that to do speaker identification and verification. For example, you just record the audio sample, and then you say you tell if it's Alice or Bob or someone else. But it's in machine learning perspective, it's called supervised because you already have the training data from each label, Alice or Bob, and then you do the classification. But for our problem, it's called speaker counting. It's speaker counting, which in the real scenario, probably in a conversation, you have some people you just met at the first time. So you don't really have their speech information beforehand. You have no prior information. So it's an unsupervised machine learning problem. But actually here, what we find is we don't need to know who is the speaker in this conversation. We only need to know that if we given two speech segments, we only need to know if they come from the same speaker or not. Therefore, we need to develop a distance model to sort of capture the similarity and dissimilarity of these two speech. And we use the cosine similarity distance. Essentially, it's just the angle of two speech feature to capture this similarity. And the common sense is if they come from the same speaker, then the distance, the angle should be smaller than if they come from different speaker. We collect some empirical data to validate this. We collected data from 10 different people, from 5 male and 5 female, and then compute this distance from the same speaker and different speaker, and then plot them in form of the histogram into the same scale. And what we find is if we have the longer speech segment, then it's very easy to distinguish if they come from the same speaker or not. As you can see in this graph, it's almost, these two histograms almost don't have any overlap. But if you have 1 second, then it has a very large portion of the overlap, which also makes sense because in the real life, if you hear someone say a very long sentence, it's much easier for you to tell who he is. If you only hear 1 or 2 seconds of the voice, it's really hard. But unfortunately, in real conversation, especially when we are very familiar with each other, we often interrupt each other from time to time. So 10 seconds speech segment is not that, it's pretty rare. And we study data collected from AT&T telephone telephone conversation, they draw this histogram and shows the median value of the speech segment is 2.74 seconds. So we empirically choose 3 seconds as the empirical unit for the basic processing. And the next step is just collect, for this 3 second speech segment empirical data to draw empirical thresholds to distinguish different same speaker and different speaker. So if I set this as theta x and theta u here, then if it's less than on this side, then I will say they come from same speaker. If the value is larger than theta u, I will say they come from different speaker. Certainly, I will make some mistakes over here. And also, empirically, we find out some of the data fitting into this region are the silence and overlap when the speech has sort of small amount of this overlap and silence. But in this problem, since essentially we are doing a speaker counting, we are not doing the speech clustering. So it's okay to drop certain not that significant speech. Essentially, we want the speech which is significantly good to distinguish himself from all the other speakers. And remember, we use pitch information in the first phase to filter out all the non-voice data. Here, for the human speech, actually it has another functionality. It can sort of tell the gender. Statistically, we have common sense. Again, male have a lower pitch than female. And then we collect some empirical data and then validate this. And we draw this threshold to say if the estimate pitch is less than 160, then he's male. If it's larger than 190, she's female. And back to this fundamental problem in this particular question, we given two speech segments, we want to know if they come from the same speaker or not. Then this is the routine to process this disposition. If the MFCC cosine similarity distance is less than this theta s, and the pitch indicates they come from the same gender, then we say they come from the same speaker.
So somehow people can get different genders and still have this cosine similarity thing come out to be similar. Can you get like that test for similarity report they're similar even though they're different genders?
I think I collect the data from 120 user identified, but definitely, yeah, some people, if I do a much larger data set collection, the situation you mentioned will appear. Then our current approach probably cannot.
I suppose you just threw out like and the pitch indicates they're the same gender as the test. Then is it just as good? Like, is your test less accurate if you throw out the and pitch says they're the same gender? Suppose you just make the test be if the MFCC cosine similarity score is less than something.
Yeah. I think I got your point. So if his speech, usually in a conversation, he will say a few sentences, not only one. So if the situation you just mentioned is keep constant, then the algorithm, I think that my algorithm cannot solve this problem. But if it's not that consistent, sometimes there are different
I'm
people.
asking a different question.
Yeah.
I think I'm just saying, like, you know, for your rule for is it the same speaker?
Right.
You have a second condition, and pitch indicates they're the same gender.
Yeah.
Suppose you just threw out that condition and just used the first condition. Maybe the test would be just as good. Maybe. I'm asking you, is it?
I didn't.
Yeah. What's
Well,
counterintuitive
because-
is no. Yeah.
Go ahead.
So what's a little bit counterintuitive is you think that if you have this feature vector for MFCC, that if two people are of different genders, then that feature vector should have a large angle.
Yeah.
Whether or not you use the pitch. So the question is, why are you using the pitch?
So-
If people of different genders have a large difference in that feature. Or maybe that's not true.
Did you get the logic?
That's exactly my question.
Maybe it's not true. Maybe people.
If they
pitches
have a
like that.
different gender, then yes.
No. So when I ask you, the situation where the pitch is different, meaning different gender, but MFCC are very similar. Did you see that or not? You said no. If you said no, that means this pitch thing can be removed.
Oh, sorry, I think I answered
condition.
wrong. I answered
So
wrong.
that's,
Yeah.
that's
Like completely yes and no in this
Okay.
topic, right?
all right. Good.
So what's the answer to the question?
The answer is, let me try to remember. If they, so the person, usually the pitch of the same person is consistent, but the MFCC, the self distance from the same person in terms of MFCC could be very large sometimes.
But
That's
that's
something-
not as
Right, but that's not common. So in that case, I will drop that speech segment. As long as the speech in terms of MCC is close enough, and then again, the same gender, then I will merge, I will classify this come from the same speech.
So you're saying it can be true that people of different genders can have a low, or similar MFCC scores?
It's also possible.
Did you see that or not?
Very rare, but I see it.
You saw that.
Right.
Okay. Then that answered all the questions.
Yeah.
Go on.
Yeah, that's sometimes that's when the error happens. Actually, sometimes I overcount, sometimes I overcount, sometimes I undercount. Yeah, because there's no real consistent scientific model for each person's speech. So different people say, when they say this the same word, there's a scientific model behind it, how you pronounce it that word. But when I just give a talk or give a sentence, some words have, even for the same person, it's very hard to get consistently unique feature characteristics. Yeah, that's what I'm trying to say. Yeah, so if the cosine relative distance is large, then the threshold or pitch indicates the one male, one female, then we say that come from different speaker. Else we are not sure, we just drop. So this is a simple conversation example. Let's say we have three speakers. Speaker A say a few sentences and interrupt by B, and then interrupt by A again. And then speaker after silence, speaker C say something. And this is a conversation, have some silence and overlap. In our unsupervised speaker counting process, essentially have two phases. In the first phase, it's pre-clustering. What we're trying to do is we try to merge the adjacent speech segments from the same speaker, because the longer speech segments we have, the easier we can distinguish if they come from the same speaker or not, as the previous cluster of the histogram we showed. We just do one pass. We didn't do iteratively algorithmic clustering algorithm. So we segment this conversation into 3 seconds chunks, and then we pre-cluster. If they come from the same speaker, we merge, and keep going. If they come from the same speaker, we merge. And at the end of this pre-clustering, we have this pre-processed speech, the conversation. And then in the second phase, we do counting. The rule is we only admit a new speaker only when its speech segment is different from all the people we already count. And if we are not sure or uncertain for a few speech segments, we just drop. So since we already filter out all the non-voice data, so we assume the first speech segments come from the same speaker. And then for the second speech, if we are not sure, we drop it. Different speaker, we count it as a new speaker. And then same speaker, different speaker, we merge. Not sure, we drop. Different speaker, and then we count it as the third speaker. And eventually we counted there are 3 speakers in this conversation. So we did a single group benchmark results. If you should be very familiar with this table, because that's just that happened.
Table here.
Yeah. Actually, I want to acknowledge many people participating in this, including Yan.
I think I look like a phone in that picture. 1, 2, telephone.
Yes. So yeah, 10 people participate in this. Yeah. experiments, I assign each one person actually magazine paper to read a few sentences, read one by one. I deploy 7 smartphones in this experiment. They are placed in different places. 4 smartphones are placed on the table and 3 smartphones placed in their pockets. And we use the error count distance, which is defined in such a way. It's the difference between the estimated speaker count and the ground truth. So we test the performance when in terms of the different number of speakers, and we find first we test if the phone's position matters, even all of them are placed on the table, and we find out the result is pretty consistent no matter how many different speakers enroll in this experiment, which means the algorithm actually scales. And also we find actually the phone's position in this table is not too important for this counting performance, because each phone can pick up certain people's speech with better audio recording than the other people. And also in this graph we're trying to study if the phone's placement matters. And as expected, the phone placed on the table have a smaller error count distance than the phone placed in the pocket, because your trousers essentially mute certain of the audio, raw audio sampling, and then decrease the audio, the quality of your audio recording. And
so these tests were like each phone tried to do this test of how many people to discern separately, right? Like you didn't somehow combine things from different phones? And
not simultaneously, but this graph actually shows if you can sort of have all the data, have the speaker count from all the phones, then do the median or the mode, make them collaboratively work on this problem, then the error count distance is smaller than the mean of these individual results.
But it seems like, okay, so some collaborative thing, when you get to have the data from 7 phones, it's like a completely new algorithm. Like I mean, you described an algorithm one phone does in terms of the pitch and the similarity score of different utterances. But if you have the data from 7 phones, right, you have to have developed some completely new algorithm, I think.
If it's synchronized, I would say probably.
Well, you just ran the raw analog data through the algorithm. You understand this?
No, so we have 7 phones.
Right.
They all record the same conversation, right, and then they individually.
Right. But you're getting a different waveform because of the placement of everything, so we may come up with a different answer.
Right. So if I take
7 waveforms, right?
Right,
and you can try to look for all, there's all kinds of structure in the fact that there's 7 processes sampled.
But they need to be synchronized when they're recording.
You didn't do any types.
Otherwise, I need to.
So what did you do to make a better collaborative result?
Yeah, I guess, right. So when you have a number of speakers there, I guess on the right side is like 8. Right? And then you have mean, median, and low. You're just selecting that from the 7 results.
The mean.
So what is your collaboration?
Collaboration is just to take the median of the estimated error count.
Okay.
It's just
all right.
all the modes.
There's no.
All the 7 phones.
Okay. And that's better.
That's better.
Okay.
It's not clear.
Actually, in this year, Mobisis, there's a paper they develop a system try to synchronize the microphone from different smartphones.
It's not clear. If you just look, if you have the blue phone on the left, that's always error count 1. And then if you take if you use the collaborative results, sometimes it's worse.
The problem is you don't know if the blue phone is the good one because it's not giving
I know.
error count.
I'm just saying. Yeah, I know. They're saying that there's some phone that's always good, and then if you add more phones.
Yeah, that's possible. Actually, in this experiment, I use
No, but
all
the chance of getting an error count 3 is pretty low. It's not clear that the collaboration is helping you that much. I guess you're right. It keeps you from getting a bad result, but it doesn't necessarily make a result.
Yeah, probably some of the phone have, probably some phone, the microphone circuit has something to flow. Yeah. We also do multiple groups benchmark experiments. We basically separate people into 2 or 3 groups and assign each group one phone on the table and one phone in the pocket. And then they start to talk simultaneously at the same time. Each group, the phone from each group will report the estimated speaker count. And in this scenario, for the total number of speakers, we just aggregate simply the summation of the estimated speaker count from different groups. In this experiment, what we find is a little bit interesting is the phone placed in the pocket actually give slightly better results than the phone on the table because it's quite localized event. And then if the phone is placed on the table, sometimes it will pick up some voice from the louder voice from the people which have a louder voice from the other group. So it will overcount the number of people. But in this particular situation, the phone placed in the pocket will sort of mute that effect, the human effect. We also did the large-scale cross-sorting efforts. 120 users contribute over 1,000 minutes audio data. These experiments happens range from private indoor environments such as home, office, kitchen, to public indoor such as restaurants, food courts, coffee shop, shopping mall, to outdoor environments such as plaza, parking lot, patio. And the average error count distance range from 1 to 1.83. All of them are between 1 and 2, which for social sensing application, which is reasonably good. So here's the lessons we learned from this project. The speaker count can be estimated on the phone in an unsupervised manner, which means we don't need to do the extensive calibration. We don't need to collect the speech data from each individual person. And also the speaker counting technique can enable a number of social sensing applications. For example, crowd estimation, social isolation detection, event engagement detection. So that's no need to report the status manually. And also for the accuracy, we see that we have the best results for the private indoor and worst results in outdoor because noise in indoor is just the highest. And finally, we need to develop some low-cost noise cancellation technique to improve the accuracy. To summarize the work I've done during the past 6 years, there are 2 parts. One is I deploy some ambient sensing infrastructure, the sensor network, and also to use the personal wearable device such as smartphone to unobtrusively learn human context, to seamlessly monitor people's physical activity and social activity no matter where they are, including the counts, location, trajectory, speaker counts. And all this information will contribute to the connected smart house. Finally, I want to thank all my collaborators, including Yanyo, Rich, Wade, Xiaodong, and also Jin, Robin, Emiliano, and also Ben, Rob, Su, Gang, Facial, and Minchen. Especially, I want to express my sincere gratitude to Yanyo and Rich during the past 6 years. They are just like my mom and dad as well. And also thank Ben and Rob. Rob is not here, but they try to regulate my programming habits. I really appreciate that. All right, thanks for coming. I'm glad to take your question.